Hello and welcome to our webinar on scenarios for validation of ADAS and AD. My name is Thorsten Püschel, and today my colleague Michael
Hi.
and me will show you how you can efficiently create, import, generate and edit scenarios for the dSPACE simulation solutions. But before we start our deep dive into traffic simulation and the capabilities of the dSPACE simulation solutions, let me briefly introduce to the topic. As you know, the automotive industry is currently in a phase from switching from level 2 to level 3. With this switch comes an increased complexity of the system because of more sensors, but also because of more complex functionality of the driving function. To test this and to finally master a SOTIF-compliant validation process, which is required for homologation, it is required to run millions of test kilometers. To achieve this, simulation is key. Software-in-the-loop simulation as well as hardware-in-the-loop simulation. Therefore, dSPACE provides an end-to-end simulation tool suite enabling verification and validation of ADAS and AD in software-in-the-loop and in hardware-in-the-loop. Besides the software-in-the-loop and hardware-in-the-loop simulation platform, which is, by the way, not the main topic of this webinar, you need simulation models to set up closed-loop simulations. dSPACE provides with AURELION and ASM all models required for ADAS AD simulation to simulate the ego vehicle dynamics, to simulate the sensors and the traffic and scenarios. A huge advantage of ASM and AURELION is that these models and the operation tools and the SIL simulation platform are ISO 26262 certified. Therefore, you can exclude these tools and models from your certification processes, which are required for using simulation in homologation, as dSPACE has already done this for you. With our models, you can work on applications up to the highest ASIL level, level D. One crucial topic in setting up closed-loop simulations in SIL and HIL environments is the interfacing with the system under test. With AURELION and ASM, interfaces on different levels and protocols can be implemented. The models provide, for example, OSI ground truth according to the ASAM OSI standard. Or you can use the ASM ground truth sensors to generate virtual object list data to be sent on simulated CAN bus or simulated Ethernet. And finally, our physics-based sensor simulation, AURELION, simulates sensor data on raw data level for camera, LiDAR, radar, and in the future also ultrasonic. Here we just talked about the generation of the required data for interfacing with the system under test by the model. dSPACE, of course, also provides sophisticated solutions for the required electrical interfaces in our hardware-in-the-loop simulators, ensuring synchronicity while mastering also high bandwidths. But let's come to the main topic of this webinar, the simulation of the environment and the traffic scenarios. Scenarios play a crucial role in verification and validation and of course in virtual homologation, as you need to make sure safe operation in all possible situations. For designing the right tests, you need the right scenarios that sufficiently cover the intended ODD. dSPACE therefore provides different means to create, generate, import and edit scenarios to support you in your SOTIF-compliant verification and validation activities. First, we provide editors with which you can implement and edit scenarios in an interactive way to set up scenarios according to your requirements or to expert knowledge and experiences that are available in your company. With requirements-based scenarios, you will only cover a small portion of the scenarios required for your ODD. If you really want to run a ADAS AD simulation in large scale, much more scenarios are required. One possible approach is to increase the number of simulation scenarios in your test campaign by importing scenarios available in public databases, making use of standards OpenSCENARIO and OpenDRIVE. Finally, you should also make use of experiences and knowledge you gained from test drives in the real world. By analyzing the data recorded in your test drives and virtualizing the experienced scenarios, you can extend your scenario databases and additionally increase trust in your virtual testing as you include relevant scenarios that occur in the real world when driving with a tested function. including all the complexity and realism of the real world. If you continuously run this process and complement your scenario library based on test drives, you can continuously reduce the unknown risks and therefore build up a solid safety argumentation for homologation. For traffic simulation in verification and validation, there are also other approaches possible, which are not based on logical scenarios. Here, dSPACE works together with partners, for example, to easily set up co-simulations to simulate reactive traffic or abstract scenarios or AI-driven traffic agents. However, in this webinar, we focus on discrete logical scenarios. So let's go through the different approaches step by step. And to explain on our scenario editors, I hand over to my colleague Michael Kluge to explain you the capabilities of setting up scenarios in our editors.
Thank you, Thorsten. Thank you for the great introduction and overview, and I will continue with some demos. In the first part of my presentation, I will focus on synthetic scenarios and their creation. In our experience, requirements-based testing requires exactly those types of scenarios and roads. That's why our editors have been designed to make the creation and editing of such scenarios as intuitive and efficient as possible. To demonstrate this, I will create a simple scenario, simulate it on the dSPACE VEOS simulation system, and visualize it with AURELION. To make sure that I will address all important topics in this learning connection, I pre-recorded the following demonstrations a few days ago. This should also make sure that I stay within my time limit and there's enough time for the Q&A part at the end. The starting point is our product Modelesc as the central parameterization tool for the ASM models. It allows the graphical parameterization of the vehicle, for example, its mass. Today we focus on scenarios and roads though. I start by creating a road network according to the requirements for my ACC driving function. It shall work in highway entry situations with a road radius of 200 meters. Therefore, I start by defining a reference line with this radius and a suitable length. In the second step, I update the lane configuration as defined in the ODD of my driving function. I define one additional driving lane on one and the entry lane on the other side. The entry should end smoothly after 100 meters and the road markings should look like on a normal highway. All those properties in the road network can be configured in the road generation module of Modelesc, which also provides a visual preview of the road itself. Now that I have my road with a specified curvature, I additionally need to ensure a consistent overall network. To do this, I add an intersection to merge the highway with the entry lane. I add 2 additional roads to the network, 1 entry lane and 1 straight highway section, and configure them just like the first one before. All roads and junctions can be interactively positioned in the road network view. Alternatively, exact values can be numerically set in the property grid or via the Modelesc automation interface, for example, from Python. The junctions can be considered as flexible connection elements which adapt to the connected roads. The junction connection points can flexibly be connected to surrounding roads and their properties can automatically be adapted. More detailed parameterization is supported by a dedicated junction view. Here and also in the road view, I can add some finishing touches to my road network. I'm able to add objects and signals from the integrated traffic object library, which contains additional information like bounding box dimension, signal types, and 3D geometry for a visualization in AURELION. It is also possible to place custom markings to the road surface, which is especially useful for junction areas or road work situations. The properties of these so-called free line shapes can be configured just like the lane border markings. After configuring all necessary elements, I now need to provide information on how traffic participants can move through the network. This is done by selecting the connecting points that should be contained in the route. Depending on the number of routes and the complexity of the road network, it might be advisable to define individual names for the routes. As the final step in the road creation, I can now save it as a part of my project. Similar to the road creation, I can now define a new scenario which contains the behavior. A scenario contains definitions for the ego vehicle and the additional traffic participants. First of all, we have to reference the road network we just created, as it contains the routes we will be driving on. In each of the nodes of the scenario, I can set the behavior in lateral and longitudinal direction. For the ego vehicle, I just have to update the velocity and it should just follow the lane. For the first traffic participant, we call them fellows, I select the second route from the network and update the initial position, velocity, and target lane. If no changes should be applied from one node to the next, I can also just set the behavior to continue. To make things a little bit more interesting, or if it is part of the requirements, I can easily add more fellows to the scenario. For the second one, I'd like to use a different vehicle, which can be selected from the traffic object library. This fellow should drive relative to the ego vehicle. That's why I changed the longitudinal and lateral behavior from an absolute to a relative type. I'd like the vehicle to stay 10 meters in front of the ego and one lane to the left. As this should not change during the scenario, I can remove the second part of its behavior definition. I now have to update the transition condition of this node so that it will be valid for the complete scenario. Now that I'm done defining the traffic participants' behavior, I also save it to my project. Obviously, there are many more behavior and road definitions possible in Modelisk, which I will not address in this short presentation. One really helpful feature of the Modelisk roads and scenarios are the alias variables. Those can be defined as an additional layer to allow easy and well-defined access to central parameters. In my example, and according to the test requirements, I add the velocity of the ego vehicle and the longitudinal distance of fellow 2 as alias variables. It is basically possible to select every attribute in the scenario, but for some it might not be very useful. To easily identify those variables later on, it's advisable to set a meaningful name and even a comment or description. If applicable, you can also define lower and upper boundaries for the variable values. Such knowledge is usually in the domain of the scenario designer in consideration of the scenario requirements. Those alias variables are designed to be used in Modelisk testing feature and in SIMPHERA, which will be shown later. Especially for an optimized value distribution calculation and an efficient test execution, intelligent variable boundary definitions are crucial. Now that both road and scenario have been defined as of our best knowledge and based on the requirements, we should take a first look at the results. As a scenario definition usually needs some iterative adaptations, we have implemented the Modelisk scenario preview. This extension can be downloaded free of charge for owners of the ASM traffic license and provides a quick preview of the road and scenario. It can be started directly from Modelisk and performs a pre-simulation without the need for Simulink, VEOS or Escalexio Hill system. The user can scroll back and forth through the scenario without the need for a full scenario restart. It also provides some measurement capabilities to optimize scenario attributes or transition condition values. I'm actually pretty happy with the results of the defined scenario, but I'd like to add another fellow in front of the ego vehicle. To do this, I quickly switch back to Modelisk, make a copy of an already defined fellow 2, and modify both the appearance and some of the relevant parameters. As soon as this is done, it's just a matter of seconds to update the scenario preview, where I can now see my new fellow 3 in front of the ego vehicle. And if you're wondering why my ego vehicle ignores the other fellows, I have just not activated the dSPACE ACC soft ECU. The actual vehicle braking will in any case be done by the driving function that should be tested with this scenario. Last but not least, let's now take a look at the scenario in AURELION. Therefore, I switch to the AURELION Manager, which allows me to synchronize the active road and scenario from my Model-S project to the configured AURELION instances. I currently only have one local AURELION on my notebook, which will show a 3D representation of the road network and all traffic participants from the scenario. The actual simulation of the ASM traffic model will be done by VIOS, to which I have downloaded both the road and scenario. As soon as the synchronization is finished, I can start the execution of the scenario on the VIOS system. From here on, you can, for example, perform physical sensor simulation, tasks with AURELION, or define additional scenarios. Now that we have learned how to create synthetical scenarios based on requirements for the driving function, we can take a look at the dSPACE scenario library. In addition to the files provided in the Model-S demo projects, there is a separate set of roads and scenarios which have been created with regards to regulation authorities or traffic incident databases. Sources we have used for the creation of those scenarios are, for example, NCAP, NHTSA, and UNECE. Let's take a quick look at the scenarios which are currently part of this library in Model-S. As you can see, they basically look pretty similar to the scenario we have created before. They also contain alias variables in order to be easily used in SIMPHERA and therefore can allow a quick start to the scenario-based testing activities. Let's now take a look at just a few simulations of scenarios from the database. The first one focuses on an AEB system in an urban environment with parking vehicles. Again, obviously, with no soft ECU AEB enabled. The second scenario is pretty similar, but now the vehicle under test is the one leaving the parking lot. A good system should at least warn the driver of the approaching vehicle or even initiate a brake maneuver. Number 3 is a well-known highway cut-in situation. This time with activated AEB soft ECU to emulate the desired vehicle behavior. Last one is from the pool of NCAP proving ground scenarios, in this case backwards driving with focus on detection of a VRU, vulnerable road user. AURELION already comes with a set of multiple NCAP targets which can be used for those kinds of scenarios. Please contact us if you're interested in this scenario library, which we are continuously improving. Last but not least, I will talk about the possibility of importing roads and scenarios that are available in the OpenDRIVE and OpenSCENARIO standards. dSPACE has been active in the ASAM projects for defining and developing these standards for quite some time. I myself have also been active in both OpenDRIVE and OpenSCENARIO, and I can say that dSPACE has acquired a very good understanding of these standards and their application. As part of the learning connection, I will show a conversion from an OpenX-based scenario library to the formats we use in our simulation environment. The source of my presentation are scenarios in the ALKS automated lane keeping system context, which have been published on the official GitHub ASAM open source platform. There are obviously many more OpenX-based scenario libraries out there, but that's the one which can very easily be accessed. I just clone the repository and will use it for the demonstration of the conversion. To get an impression of the scenario, I use a tool that is currently under development at dSPACE. It provides a preview of the OpenSCENARIO file and contains an automatically generated 3D preview of the road network. We currently use the open source scenario engine ES Mini for the calculation of the entities. Similar to the Model-S scenario preview, I can just play the scenario forward or rewind to the interesting sequences and focus on one of the entities. The ego vehicle should stop before hitting the first target. As an experienced user of the standard, I can even change some contents and get an updated preview. In this case, I moved the obstacle targets much closer to save us some time later on. While the preview is updated, I quickly start the conversion of the OpenSCENARIO file. For that, I use an engineering solution in MATLAB that is available for customer projects. This automatically converts the contents of the OpenSCENARIO file and the referenced catalogs into the dSPACE proprietary scenario format. Let's quickly switch back to the OpenSCENARIO preview. As you can see, the two targets are now much closer to the start of the road. We should see the same behavior in the converted scenario later on. Let's now take a look at the progress of the scenario conversion in Modelisk. As a first step, the reference OpenDRIVE road network is automatically converted to the dSPACE road format by a feature included in Modelisk. The contents of the scenario are created by using the Modelisk API. We see the ego, the lead vehicle, and the two blocking targets with properly assigned traffic object types. The first target also contains the updated 100-meter distance to the start of the network. Now that the conversion is finished, I can simulate the scenario and visualize it in AURELION. The actual process is identical to what we have seen in the first part of my presentation. I triggered synchronization from the AURELION manager and downloaded the contents of my Modelisk project to the selected simulation platform, in this case VEOS. As soon as AURELION has been synchronized, I can start the execution of the scenario from Modelisk and take a look at the final results of the scenario conversion. In this case, the original OpenSCENARIO file included the activation of an AEB system, so the ego vehicle manages to avoid a collision with the target. My last topic for today is the development of the native support of OpenDRIVE and OpenSCENARIO in our automotive simulation models ASM and in AURELION. Although we have a working conversion solution for these standards, as you have just seen before, we are convinced that a direct usage of those formats is a necessary next step. Even if the conversion approach works in many cases, you can never achieve full compatibility or a lossless transition from one format to the other. But this is actually expected by our customers, so they can be sure to integrate OpenX-based scenario libraries without any conversion losses or problems. Additionally, the standards of the ASAM simulation domain like OpenDRIVE, OpenSCENARIO, and OSI grow closer together over time. In order to raise the full potential of this family of standards, a native support is mandatory. The OpenSCENARIO preview I used before just gave a small glimpse on what we are currently working on. We internally have a real-time capable simulation model which directly uses OpenSCENARIO and OpenDRIVE files for scenario execution and outputs an OSI stream. AURELION is partially already supporting those standards for visualization and sensor simulation, and we are working on their integration in SIMPHERA. We plan to provide more details on the progress next year, so please stay tuned for exciting updates on this topic.
Thanks, Michael, for these exciting insights. So now let's talk about real-world scenarios in simulation. Why is it actually a good idea to virtualize real-world traffic for verification and validation of ADAS and AD? Well, by continuously scanning your test drives for interesting scenarios, you can complement your scenario library and obviously increase test coverage, also with real-world corner cases. If you have experienced issues or disengagements of the AD in your test drives, you might want to analyze these issues in simulation and add this scenario to your regression tests. The real world is complex. You also want this complexity in simulation for realistic tests. Before using a simulation for verification and validation, you should make sure that your models are accurate enough for the intended purpose. By comparing a real-world recording with a simulation of exactly the same scenario, you can prove accuracy of your models, especially your sensor models. Last but not least, you can reduce the unknown risks and gain knowledge on real-world traffic by continuously analyzing your test drives in a data loop as shown on the previous slide. This is especially important for a SOTIF-compliant testing and validation process. To support our customers with that, dSPACE provides tooling and services. The Traffic Virtualizer is a tool by dSPACE to virtualize real-world traffic recordings. It creates an exact closed-loop capable replica scenario to recreate the recorded scenario in simulation. Additionally, a logical scenario is created that also proposes parameters to be varied in scenario-based testing. With that, you can create hundreds of concrete test scenarios and test cases just out of one real-world scenario, and even makes the scenario more critical to create further corner cases. The scenarios are ready to be simulated in SIMPHERA, ASM, and AURELION, and are also available as OpenSCENARIO, so that you can use them also in other simulators. The tool extracts also parameters from the scenario, so that you can do statistics on the traffic experienced in the test drives. The traffic virtualizer is now available as an early access version. So if you are interested in using it, just contact us. The traffic virtualizer processes trajectory data that can come from different sources. If raw sensor data is, for example, available, so camera data, LiDAR data, and GPS data, the data needs to be labeled. Here, our daughter company, Understand AI, offers the required labeling services and creates trajectory data suitable to be directly processed by the traffic virtualizer. This process also creates a road model, so an OpenDRIVE file based on the raw sensor data. On the other hand, our customers typically also process object list data generated by the onboard perception. So if you record the data, for example, from the vehicle bus, conversion scripts are applied to bring the data into a unified format to be processed by the traffic virtualizer, and then we can make a scenario out of it. This can be done completely independent from dSPACE, as a tool can run on your premise. With this method, also other data like drone recordings can be processed. So, enough slides for now. Let's have a look at the real tooling and the workflow for traffic virtualization. So here you can see a recording that we've done with our sensor car on a highway near Paderborn. So you can see the camera video and the LiDAR data overlaid there. And in this recording, there is one interesting situation that we want to reproduce in simulation. As explained before, the first step is to do labeling. Here, we use the labeling services and labeling tooling from our daughter company, Understand AI, which you can see here. So we have the LiDAR data on top, and in parallel to that, the camera data below, with all the highly automatically labeled bounding boxes shown there. And yeah, you can go through the different frames and see how the data was labeled there. Based on this data, the scenario description file with all the trajectories included is created, which you can see here. So this is just a JSON file with the trajectory data included, some information on the timestamps in there. So that's this list here. And below in this file, we see also the trajectory data with the XY position, the Z position, and some additional information. So based on this trajectory data, we can now start the virtualization of the traffic with the traffic virtualizer. So this is a tool. And the first step is to import the scenario description, the trajectories into the tool. Also, we need to select a corresponding road model where this scenario takes place on. And after importing the trajectory data to the scenario generation tool, we can now set up the scenario generation. So select the JSON file again, select the road file, add a comment so that we find the scenario later on, also in the list of generated scenarios, and then just start the generation. And now the traffic virtualizer is calculating the scenario, doing some filtering, checking some data, identifying certain traffic patterns, and finally it has created the scenario as a model desk pool file. So you can see this here, and this pool file can now directly be imported into model desk. So we just copy the path of the directory where the scenario was generated to, and now import this into model desk. So now the scenarios are imported into model desk, and yeah, we can select the desired scenario for simulation. So in this case, we select the replica scenario, as we want to have in the first step exact reproduction of the real scenario in simulation. So here you see how the scenario looks like in Model Desk. So we have the definition of the traffic participants that are present in the scenario, and these definitions are basically time-based velocity profiles and trajectories. So for visualizing the scenario, I used AURELION in this case. So I started the synchronization of the scene with AURELION, and now we can just start the simulation and have a look on the scenario in simulation. And this is basically the same scenario that we have seen before in the real-world data. And now we have it available in simulation by using the labels from Understand AI and using the traffic virtualizer in the second step to virtualize this. It's also possible to have a look on the camera data and the simulated data in parallel. So you can see this here. So we have this kind of synchronized view of the scenario, and you obviously see that the vehicle that making the cutout has a different color. So this was not labeled in this case, so we didn't consider this in the scenario generation process. But it's easy to change this also afterwards in the scenario editor. So just selecting a different vehicle here in the traffic object manager, searching for the right white asset. So we choose this black car now as a vehicle that we want to use in the scenario, and just change it. Download the scenario again. Start again the synchronization from AURELION so that the scene is updated with the right geometries, and then after synchronization is done, we can start the simulation again. And now you see that the scene looks much more similar, as this geometry and the color, especially of the vehicle driving ahead of us, is very much more equal to the real recording. So what we have seen now is how we have virtualized recording of raw data using the labels from Understand AI and creating a replica scenario and having the direct, exact replication of the scenario in simulation. In the last minutes, we've only shown the simulation on a local desktop in our SIL simulator VEOS. But for verification and validation of ADAS AD, massive and scaled SIL simulation is required. And this is done with SIMPHERA, our web-based, highly scalable, cloud-ready simulation framework. With SIMPHERA, you can design and run massive parallelly executed tests in a cloud-based environment, enabling also global collaboration and CI/CD processes. It is easy to use the scenarios we prepared before in this webinar, also in SIMPHERA. The dSPACE simulation solutions ensure a seamless transition from local SIL to HIL to cloud-based simulation, and of course vice versa. Now, let's use the same scenarios in SIMPHERA that we have just generated before and simulated on the local machine to set up a cloud-based simulation and cloud-based test campaign. This is our web-based user interface for SIMPHERA. So on the left, you can see a menu with different sections, so you can define scenarios, you can design vehicles, and also set up your test campaigns. Here you see a list of scenarios that are available in SIMPHERA by default, but of course you can also import further scenarios. And now, we do this with a scenario just generated. So we use the A33 scenario again, so the scenario that we've generated from raw data before, and just copying the path to the model desk pool file again, and importing this now to SIMPHERA. So now we select the logic scenario because we want to use this in scenario-based testing. So you can see that some parameters defined that automatically come with the logical scenario. Now we use the scenario to design a test case. running multiple multiple simulations with different parameters. So in the first step, we define the test case. We give the test case a name, and then select the scenario that we want to simulate. So this is basically the one we have just imported to SIMPHERA. And also we need to select a suitable vehicle to do the test with. Here you can see the parameters that are available and also the values of these parameters. You can choose different methods how to vary the parameters. Now we just do a simple cross variation, defining the range from up to 130 kilometers per hour with 5 kilometers per hour step. Additionally, we have to somehow define when the test is successfully done. So we define a criteria to check for collisions. So just adding this, evaluation of simulation signals, and this doesn't need to be active, so we don't want a collision in the test. Now we've already defined our test case with the just generated scenario, and we can now run this test case, run these 9 simulations. And here you see how these are currently processed. So it's starting the simulation process, and running 9 simulations now in this cloud-based environment. So here you see the list of the test cases. Just as a reminder for the scenario that we look at, so this is this scenario that we have recorded in the real world. So where we have this cutout situation of this black vehicle in front of us that we have labeled and virtualized with the traffic virtualizer, and now imported into SIMPHERA. And now you can see the first test case is already finished. So this was successful, this test run. So means no collision happened. But anyway, we want to have a look on the scenario and analyze the simulation. So this can be done easily in SIMPHERA by using this analyze functionality. And in there, you have this kind of simulation player, where you can scroll through the scenario, go back and forth, and have a look on the data. So now let's see how the other test cases turned out. So in the meantime, already further simulations have been run, and here's one test case that failed. And now let's see why this happened. So at first you can check the parameter. So the velocity parameter is now set to 101 kilometers per hour. And in here you see that in this scenario a collision happens between the ego vehicle and the vehicle which is making the cutout because of higher velocity of the ego vehicle, which was the parameter that we have varied in this test case. In the meantime, all the tests are run through, and what you can see is that the first 3 tests have passed and the other tests have failed. And if you have a look on the parameters, you see that with 96 kilometers per hour ego vehicle velocity, the test was still successful, and starting with 101 kilometers per hour, the tests start to fail. And with this methodology, you can easily check for borders in your parameters and know when your system is still safe, and when the scenarios get too critical, where you have to improve your device under test or your driving function further. With that, we want to conclude this webinar about scenarios for verification and validation. So just as an overview and as a summary, we have the scenario and road editor in Model Desk so that you can set up requirement-based scenarios. We can import OpenSCENARIO and OpenDRIVE to our simulation models to easily access scenario databases, with a native simulation of OpenSCENARIO coming in next year. We can bring real-world traffic into simulation by using the traffic virtualizer. And we have, of course, a seamless transition from ZIL to HIL to cloud and vice versa to use scenarios in all your verification and validation activities. So thanks for joining this webinar, and we look forward for your questions.
Yes, also thank you from my side, and looking forward to the Q&A session.